Hello students, this is my lecture number 10 and today we will discuss the last topic of the process management chapter. In this topic, this is very small lecture where I am going to discuss how to create the process and how to terminate the process considering the Unix operating system. So we basically create a process to do some task, right? So there may be some process that I want to execute it. So whenever any process that I want to, whenever there's any program that I want to execute, first I will do what? First I will write a code and then I will save it and save that program into the secondary storage device. Then after that I compile it and save the object code in the secondary storage device. Then after that I give it the execute command dot slash a dot out. When I give the execute command dot slash a dot out, the executable code from the secondary storage device will be brought into the um, RAM or will be kept into the ready queue with the help of the scheduler program. Then when CPU will get chance to execute that program, okay, that time the process will be executed or the instruction that is written in the object code will be executed. So we write the program in order to accomplish or to perform some task. Now during the execution of any process while in the running state, during the execution of any process, that running process can create several other process. Okay, so they can create several other process by invoking a create process system call, and the created furthermore the created process, the newly created process again create another process by invoking a create process system call. So thereby you can have a series of tree kind of structure, which one process create another process and that new process create another process. We can have a series of the process created, and it can be represented in the form of the tree like as shown out here. This is just the example. Okay, now whenever a running process creates a new process by invoking a create process system call, that invoking process who is responsible for creating the another process is known as a parent process, and newly created process is known as a child process, right? So we all know that what is the meaning of a parent process now and what is the meaning of child process. So the caller program is known as a the caller who is invoking a create process system call is known as a parent process, and newly created process is known as a child process. Now in most of the operating system like Windows or Unix, the process is identified by a unique integer value known as a process ID or PID. We generally call it the PID. So every process is identified by unique name called a process identifier, which is basically an integer. Now there are various reasons like with respect to resource sharing whenever we create a process. Now it may happen that whenever you create another process, the child, whatever the parent, all the resources of the parent will be allowed to use by the children also. I repeat, whenever any process is created by a parent process, okay, all the resources held by the parent process will be allowed to be used by the child process also. Or it may also happen that some of out of all the resources that is with parent process, out of that only some of the process may be allowed to be used by the child process. Or it may happen that parent may not allow any of its resources to be used by the child process. Now whenever a process is created, okay, whenever a process is created with the help of the create process system call, right? So there are two scenarios, two things that may happen, and from execution point of view, right? From execution point of view, whenever any process is executed, right? So whenever any process executes the create process system call, it may happen that parent and child process both will execute concurrently. So say for example, I'll just show you with the help of the example. Suppose there is a process, right? Suppose there is a process name is P or parent. Okay, so during the execution of process, now say for example somewhere here it executes a create process system call. Then what happens is that there will be two branches. there will be two branches. These branches belong to P, okay, that is continuing branch, or in other words, this branch belongs to parent process, and this branch belongs to child process. So from this we can say that the child and the parent will execute concurrently. So this is one scenario. So it may happen that whenever any parent process creates a child process, it may happen that one scenario, parent and child will execute concurrently, one after another. So it may do one task, the parent may do one task. So for example, parent is finding the factorial of a number and child is finding the Fibonacci series. So it may happen that. So this is one scenario. Another scenario is uh, parent will wait for child to terminate. So it may happen that you have designated child to do some task. So child will do some task. So child will do some task and parent will wait here. Parent will wait here. So W means wait. Okay. So parent is waiting for the child to complete his task so that it can terminate the entire program. So this is the basic scenario about what will happen whenever any process will invoke a create process system call. So I repeat, whenever any process, a parent process creates another process, child process, either parent and child will work independently or concurrently to perform different tasks by them, or it may happen that it will allow the child to work for some time to complete its designated task, and it will wait for the child to terminate normally. Okay, that is from execution point of view. Now whenever any process is executed, or whenever any process executes create process system call, then what happens to address space? What happens to address space? For example, suppose at this point it has invoked a create process system call. So here it has created a system call. Now what happens to the address space? Say for example, this is the address space. There are some code and instruction, there are some data and code in the parent process. This is the memory given to the parent process, right? Now parent process have invoked a for system call, the parent have invoked a create process system call. Then what happens? A duplicate copy of same will be created. A duplicate copy of the same will be created, having same code and same data, and will be assigned to C, that is child process. So this thing will what happen in case of address space. So what will happen whenever any parent process creates a new process, a child process, it will, the child process, the content, the address space, the address space that is designated to a child process will have a duplicate copy of code and instruction that is with the parent process. Or it may happen that child process, inside the child process, it may get loaded with the new program. So for example, let us take up the same example. Okay, let's erase it. Okay, so suppose there is a parent process and there is a child process, right? So this is my parent process and this is my child process. So before child is created, parent will have a memory where data and instruction are there, or code and instruction are there. Now whenever a parent will execute the create process system call, a copy of same will be created. This is one scenario. A copy of same will be created with same data and instruction that is with the parent. Or it may happen that new set of instruction will be initialized in the child. So this is another scenario. So there are two scenarios which you have seen it. So whenever, I just repeat it, whenever a process creates another process, or whenever a parent process creates a child process, from execution point of view, parent or child may execute concurrently, or it may happen that parent will wait for child to terminate normally. Or from the address space point of view, what will happen is that it may happen that the child may have same copy of data and instruction that parent will have it, or it may get loaded with the new instruction and data, okay, based on which it has to work. So this is all about the process creation, and we have seen that we can create a process can create a child process, and furthermore that process can again create a child process. Like that we can have a tree of instruction, and each of the process is identified by unique identifier called as a process identifier. right? PID in short. Okay. So now, how to actually create a process? Which system call should I use to create a process? So in a Unix system, a Unix operating system, we can create a process by invoking a fork system call. So fork is the name of the system call with the help of which the operating system will create a new process, right? And whenever it creates a new process, what will happen? Whenever any process is created, okay, using invoking a fork system call, it will return some values. Okay, there are only two possibility. There are only two possibility for after execution of fork system call. The fork system call may return two values. One is 0 and another one is non-zero. Non-zero value is given to the parent. Non-zero value, whenever fork system is executed, non-zero value is given to the parent, so that parent will know what is the ID or process ID of the newly created child process. Okay, and it will return 0 to the child process itself. Now, these are the two possibility whenever fork system call is executed by the operating system. Right? And this is one scenario. Now to identify whether the fork system call has been actually successfully executed or not, to note that, okay, it will return negative value. So if the fork system returns negative value, then what happens? The operating system will know that the fork system call has not been successfully executed completely. Okay, so it will know that with the negative value, it will know that, okay, if fork system call has not been successfully executed. Now if the fork system call returns positive number to the parent, then it is returning the ID of the child process. And if it is returning 0 to the child, then it is indicating child that it has been successfully created, right? Now, as I've told you already, that whenever a fork system call is um, executed, there will be two parts, something like that, and parent and child process will. This is the top line is the parent, and below line is the child. So parent and child either will execute concurrently, parallelly, two different code, or parent will wait for the child to complete his task. That is from execution point of view. Now from address space point of view, after execution of the fork system call, the parent or the child may have same content. Parent, the address space contained by the parent, and the address space contained by the child, or in other words, data instruction with that is with the parent, and the data instruction with the child will be same. That is one scenario. Another scenario is child address space is replaced with some new code and instruction or data, right? So to load the address space, I repeat, to load the child address space with new data and instruction, there is a specific system called exec. So exec, with the help of exec system call, you can load into the child address space with new data and instruction, so that the child can perform some specific task. Okay, that is designated by the exec system call. So exec is also another system call which is used to replace the address space of the child process. Now there are different versions of exec, exec exec c, etc, etc. Okay, you can have a look on later on. Now after completing his task, the child may get terminated. The child may get terminated by invoking a exit system call. So it is the exit system call which with the help of which the child process will get, or not only child, any process will get terminated. So it's an exit system call. So after exiting the system call, it will join with the parent, because it has to because it's a child process and parent is waiting for it to complete its task. So once the child process complete its task, it will invoke or it will execute exit system call, indicating that its task has been completed, and will join with the parent out here to terminate the entire program. Okay, so with the help of, here in the case of parent process, it is the wait system call that will help the parent process to wait for the child to complete its task. So these are some of the system call that you need to note down. That is, some of them are fork system call, exec, and exit, and wait. Okay, so every system call has its own purposes, and these system calls are executed by the operating system in a privileged mode. Okay, so this is all about it. So let us take the example, with the programming example, how to create a process. So this is my general format, int main. Okay, and this PID is the variable where I am going to store the ID of the newly created process. This entire program itself is one process, maybe a parent process. So PID underscore T is a structure inside which, with the help of which I'm going to store the ID of the child process. So I've invoked the fork system call. I've invoked the for system call, which is returning some value, maybe a integer, or maybe a negative, or maybe a positive value, okay, or zero value. So if it is a negative value, if PID is negative value, less than zero means negative value, then it indicates that the fork system call has not been successfully executed. So that's why there is some error message. Now, apart from negative value, it may give positive value also, right? If positive value, sorry, if it returns zero value, okay, if PID value is assigned with zero value, so it indicates that for system call has been successfully executed. And returning zero means this portion, whatever you write inside this curly braces, if PID is equals to zero, if it, whatever you write inside this code, okay, that code belongs to the child process. So what this blue color region is known as a content of the child. So the content of the child can be replaced with the new code, new data, and new instruction with the help of the exec system call. And execlp is one class or one type of exec system call, and it is executing list command, ls, okay. So some command it is executing. You can, this thing can be replaced by some another code and instruction with the help of the exec. Like for example, suppose this parent, this main parent want the child to compute the Fibonacci series. So you can have here somewhere here the executable code, binary version of the compiled code. You can have it over here, that is responsible for calculating the Fibonacci series or any other work. Now in the meantime, okay, in the meantime, the if this is not the scenario and this is not the scenario, it is very obvious that if it is not negative, if it is not equal to zero, then it is very obvious that the PID contains the value, positive value, that will be given to the parent process. Now this green portion is the section of the parent that is being executed concurrently or parallelly along with the child. So these two will be get these two instruction, else if and else, this part will get executed concurrently in different address space, maybe with the help of different content, because I've used execlp out here. Okay, so this is all about the um, parent and the child process. Here in case of the green, that is parent content, okay, parent is waiting for the child to terminate this task, okay. So when child will, when child process will execute the exit system call, the control will reach over here, and then furthermore the entire system, entire main program will be executed. So wait system call, so the after completion of task, the child process will join in the wait. Then with the help of the wait system call, the parent process will able to know the return from the return from the child to parent, okay. With the help of the wait system call, the parent process will be able to know that the child process has now terminated successfully. Maybe it returns something, some value to the parent using the wait system call, okay, or through the wait system call. So once this wait system call is executed, it will know that the computer system or the with the help of this main program, the main program will be able to know that child have completed its task. And again furthermore, this exit 0 is for terminating the entire program or main program or the parent program. So this is how your child process can create another process, and in the another process, newly created child process, some another task can be done along or concurrently along with the parent. Okay. Now process termination. See, once all the tasks by the child process is completed, okay, it will terminate. And it may also happen that parent process have completed all the tasks, it may terminate. Okay, so to terminate any process, the process has to invoke a exit system call. So exit is a system call with the help of which you can terminate the process, right? Now whenever a child is invoking a exit system call, okay, the parent process will able to know that parent have exited with the help of the wait system call. So through the exit of the child process, the link will be made with to the waiting process, wait system call of the parent process, and then parent process will get further terminated. Now after whenever any child process will get terminated by invoking the exit system call, all the resources will be that is assigned to the child process will be deallocated, right? Now there are various reasons for the termination of the child. So it may happen that the parent process have created a child to do some task, right? And that task is not at all required anymore. So at that scenario, the child process may get terminated. That is one scenario. Or it may happen that the child process is given some task, okay, to complete it. Now during the execution of that, the child process uses exhaustively all kind of resources. It has exceeded the all the allocated resources. So and again demanding for some more resources. So in that scenario also, the child process may get terminated, saying that no more resources will be given to the child process. So that is another scenario. Okay, now it may happen that sometimes some operating system does not allow the child process to continue if the parent is exiting. So in that scenario, what will happen is that whenever a parent process is terminating, then all the child process will be automatically terminated. So such kind of termination is known as a cascading termination. So I repeat, whenever a child process is terminating, all the child process will be terminated automatically. Such kind of termination is known as a cascading termination. So this is all about the process creation and process termination. So you all can implement it. Okay. Yeah, so I can give you a, you can just try it that with the help of this format. Okay, you can create a process, okay, a main program, where main program has some specific task, like for example the main program somewhere here it calculates the factorial of a number, and you have designated a child process that will calculate the Fibonacci series. You can try this program later on. Okay, so with the help of the exec system call wait and fork system call. So if there's any questions, please do upload it or bring it up in the next session. Thank you so much.